Okay. So welcome to this RTL to GDS course. Any questions you have, like what exactly is RTL, and
Can you explain the flow like RTL to GDS, how we proceed with
I'm
any tool?
explaining that. Yes,
Yes.
I'll be doing that. So any other? Uh, okay. So you wanted a flow, but basically let's start with your bottom up. What exactly is the product of this? That's a chip, right?
Sir.
Yes or no?
Yes, sir.
These are all the contact points. And what is this? What do you call this?
The chip packet chip.
It's the package, correct? This is the package. The actual chip is inside it. The actual die is inside it, right?
Yes, sir.
If I zoom in, you'll see in this fashion. This is the actual die. I have a couple of more images as well. And if I, okay, I'll stick to this one. So these are all my contact points. These are all my IO points, right? Yes or no?
Yes, sir.
These are all the power rails, VDD and VSS. And these are all my blocks, or you call it as a macro. And you have all the wirings and stuff. This is the end product, right? How do you get a set of logic that, hey, this has 3 inputs, 1 output, and you are basically constraining whatever inputs you'll get based on that expected output I'll have. This is the logic you have written. This logic is converted into gates. Actually, these are all cells. NAND cells, NOR cells, these are all the standard cells. In synthesis stage, you'll generate a standard cells. Now we'll move to physical design. In physical design, you'll have the die area. Okay. In the die area, you'll do floor planning. Let's say you'll partition your, let's say this is your CPU space, GPU space, memory, or IO space, in which you'll partition. And then you'll place all of your macros, or of your logic, or whatever your design you have. This is smaller. I've given you the idea. This will be placed here in the placement stage. Let's say these are all the IO pins, and then here you have your logical cells. Whether this is timing correct or not, you will do clock tree synthesis. Once this is clear, then you'll do the routing. Okay, how will you route? How will you connect your wires? Okay. Then you have your different stage of GLS and then physical verification and sign off. Any questions till now? Any questions you guys have?
Oh, sir.
Okay, let's say mod 8 counter. What exactly is this? 0, 1, 2, 3, 4, 5, 6, 7, right? And then 0, 1, 2, 3, correct? This is
Yes,
a
sir.
mod 8 counter. Let's say in order to represent 7, how many bits is required? Three bits in binary, right? Yes or no?
Yes, sir.
We need 3 bits. So at least I have to declare my register as 3 bits. Go down to 0, count. TNT. Now I'll just give you a high level micro arc of my counter. We'll have a D flip flop. And then this is at reset, it will go to 0. We'll start with 0 at reset. This is my count of 3 bits. Here is my clock. And then I'll have an adder. I'll just connect this adder here. So this is my your mod 8 counter. This is a mod 8 counter schematic in which I'm using a flop, I'm using an adder. Now I'll translate this schematic into RTL code. How will I do that? It's very easy. Let's say I'll name this as K1. In order to represent an adder, you can write in data flow assign K1 equals to count plus 1. This is my adder. And for a flop, you can use always at the rate passage clock. And then if reset, you make the count as 0. Else you make count equals to K1. That's it. This is our RTL code. Now this RTL code, we'll simulate it. We'll write a test bench around it to test it. And now companies are also using formal verification tool. We'll not be doing it here, but we also have formal stage as well. In order to remove the bug, in order to catch the bug and resolve it. That is what we do in this simulation stage or design verification stage. Once this is done, once the RTL is clean, then we'll send it to synthesis. Whatever logic cells we have, standard cells we have, we'll use the standard cells and translate into a netlist. Let us first do this part. So this is the projects folder. I'll go to RTL. I'll open this guy. I believe older code is there. I'll just remove this. Then let us write module your mod 8 input clock reset output reg 2 down to 0 as we saw 3-bit count module. I'll declare a wire. So I need a wire of 2-bit, which was K1, and then I'll write my adder K1 equals to count plus 1, and then I'll write my flop always at the rate of each clock. If reset is high, my counter should move to 0, else my count should be K1. Basically, you can also replace this K1 to count. We'll see this can be done during optimization. So this is my RTL, right? Any questions here? Just to make folders clean, I am moving it to a different, as you'll see a lot of clutter in this directory. Once we start simulation, this is my test. I'll remove this dummy code, and this is my design. So module top is my test bench, and I want to write a test bench around it. I want to write, yes, test bench around this mod 8. Why reg? Why inputs are reg? Why inputs are wire? I believe you guys need to tell me this. Why we are doing this? Anybody? Why I'm writing input as wire and why I'm writing output as reg? And module. Let me generate a clock with periodicity as your time period is 10. Reset was active high. Let me wait for some time. Then make reset as 1. Again, wait for some time. Make my reset as low. And then I'll wait for, let's say, hash 500. I'll finish. That's it. This is my simple test bench. Now, how do I simulate it? How do I run it? We'll invoke a tool. Once you invoke tool, you'll have to do compilation, which will check for syntax errors. Then we'll do elaboration, which will do all the connections. And then we'll simulate it. We'll see what is this make file later. I'll just run the make run. So here I'm using Questa from Mentor Graphics in order to simulate it. And if I want to see the waves, I need to add. So I want to see count, clock, and reset. Add to wave. The see it is added. We'll change the radix to unsigned, and then here run. And run for 10 microseconds, picoseconds, but I'm doing run -1. It will run throughout the simulation until and unless it reach $stop or $finish. If you see the waves, you'll see, okay, count is X. Let us see what happened. Test.v, ENT, and you can see the RTL. Let me also append K as well. Vlog, so I'm writing the command. I'll compile the RTL. I'll compile the test. Solution done. vsim top. I'll add all the signals. Add wave -r star, which will give some detail in order to debug it. Which at K is X. Certainly my K is also going X. So I'll do one thing. This is not a Verilog class, so I'll just remove all of this and write a normal. Okay, come on, this is not GVim. Again, compile, elab, add the waves, and then run. Oh, my output is red. X. Did I give reset? Yes, I give reset. Oh, okay. Got the issue here. This is synchronous reset, and I'm giving asynchronous reset in my test. Yes. If you see, I'm giving asynchronous reset. I'm not waiting for the clock edge. If I give the reset, I have to at least wait for the edge of the clock. Okay, I'll wait for 2 edges. Plus edge clock. And if I run again, yes. See here, this is my mod 8 counter. You can see, right? 0, 1, 2, 3, 4, 5, 6, 7. Again, roll back to 0, 1, 3, 4, 5, 6, 7. Now, how do you know, how a verification guy will know that I have tested all the feature of it? Let's say if you are in class 5 or class 6, how the teacher will promote you to class 6? Let's say you're in 5, how do you teacher will promote you to class 6? You have a metric system, right? What is the metric system? Exam. Let's say if you get 50% in that exam, you'll promote from one class to other class. Similarly, in your verification, we have two metric systems: code coverage and functional coverage. Code coverage give you qualitative analysis. Functional coverage will give you the quality. This is quantitative analysis. This is quality of this. Let's say my functionality is your whether I can able to collect the garbage correctly or not, whether the interrupts are getting triggered or not, whether the basic bring up function you're simulated correctly or not. These are all the functions. Let's say I'll give you one example of a router, 2x2 router. This is source address 1, destination address 1, source address 2, destination address 2. What are the combinations you'll test? You'll test only source address 1 to destination address 1, source address 2 to destination address 2, and you'll say that, okay, yeah, I've tested it out. How do you know that there are multiple paths? You have to write coverage. There is one more path, source address 1 to destination address 2, source address 2 to destination address, source address 2 to destination address 1. How do you know that you have not missed? Because now the designs are so complex. So in order to give a sign off that yes, I am done with the verification, whatever design you have, whatever RTL you have, it should go to the other stage, which is synthesis. We do coverage. So, okay, this is question. Any questions you guys have? Any questions? So I use this. Let me use this as well. Let me show you cadence too. Let me use, let's say, I'll use cadence for coverage. It will simulate, elaborate. It will open this cadence simulation tool. Exilium, this is the same design. And let's say in DUT signals, I'll add waveform. This is my waveform, and I'll run. See, same thing you'll get. So you don't have to worry about which tool you're using. You don't have to worry about that. Now, when the simulation is done, I want the coverage, whatever portion is covered or not. For that, it will generate a database. And you can load the database that we see. Okay, created. We use a tool named IMC from Cadence. Sim already have it inside the same window. Let me load. Here you can see it's 100% covered. So you'll see toggle analysis. So clock is being toggled, reset is being toggled, my count is also being toggled. All the 3 bits are toggled. So this is my 100% code coverage. For functional coverage, you have to write. That is a different part of discussion. Let's say we are happy. And see, all of these 4 files are created. Now to make it clean, I'll just do make clean. That will remove all of those. So once I'll say that I'm happy with my RTL design, I can go to what is the next step? Synthesis. This is my synthesis. So in synthesis, what we'll do, we will use this library file. This is my standard library. Whatever code you have written, it will convert it into a standard cell based on the technology node. This is 45 nanometer tech node. And in the synthesis stage, whatever code you have written, it will convert and create a netlist. So let me open this guy. This is my RTL code. See the RTL code. And then let's wait. Within synthesis and see output, and this is my netlist. Let you see mod 8 counter. This is my high level code. Now this is converted into netlist. It's using this D flip flop, NOR, XOR. These are all the standard cells. Makes sense. If you want to see it in the GUI, you can do that. I believe it's GUI show. Yes. So these are all the standard cells which is being used in the design, and I can view it. It's using NOR, D flip flop, some G75 library. So this is your entire mod 8 counter. We have clock, we have reset, and we have this 3-bit output. This is my synthesized logic. Synthesized netlist. This is the netlist which will go further. RTL is done. Till this stage, RTL is done. Now we'll use only netlist. Any questions you guys have? I'll go back to the drawing board. Now we came from the specification. The specification we translated into an RTL, right? Yes or no? Dot B. Now once we do synthesis, it creates a netlist. Dot B. It is also dot B. Netlist. How do you know your whatever RTL functionality you have, it is correctly translated to the netlist? All the functionality features are translated. It is not optimized because tool does optimization. How do you know? There comes the picture of LEC. You guys know what is LEC? Now after each stage we do LSC now. From here we'll do LSC at each stage. What is the full form of LSC?
Logic equivalent checking.
Logical equivalence check. Correct. Whatever your intent we have for the RTL, the same intent should be translated to the your netlist. So for LEC, let me show you. We'll use. Okay, this is done. Let me just close this guy. The synthesis done. We'll go to LEC. So just make run. That's it. To invoke everything. Conformal is the tool from Cadence, which will do logical equivalence check and see. It's done. There's no violation. Logical equivalence is done from the RTL. Since it's very small design, that is the reason it didn't cry. And we also have formality from this guy. Let me see if the formality works here or not. Formality is from Synopsys. So this is the same window. See, we have this verification run. We have your LSC checks. So you can either use formality or conformal, whatever. It's up to you. You should be tool agnostic. You shouldn't think that okay, I need to work on only in this tool and I'll be stick to this tool. No, you should know what exactly is the intent. It's just similar commands. Just here and there you have changes. Okay, once LEC is done, let's say there is no violation, then you'll say that yes, my synthesis stage is complete. And nowadays the devices are so complex to save time and to not go through that respin. Let's say whenever you create a chip and it's not working, billions of dollars are lost. The companies are also introducing GLS here as well, gate level simulation. Whatever netlist you have, this is my netlist. You remove the RTL and put the netlist and run with the same test. This is the stage in which you'll also find bugs. In RTL, you're not able to catch it, but in netlist, you might. This is one stage in GLS. Earlier, GLS was post PNR. Once the PNR is done, timing details are extracted based on the standard delay format. SDF file, you will annotate, means you'll mimic whatever netlist you have, your gate will mimic. Let's say you have a flop. There is a clock to Q delay. Whenever clock is triggered, D to Q, there is a delay. There are billions of your flops. A lot of delay is introduced. So you annotate that delay and run the netlist. You do post PNR GLS. Earlier, this was the case. Now these companies are also using it. We are not going to do GLS. After synthesis, we'll move to what? Direct PD. We still have GLS, DFT, ST as well. But for this demo, let's move to PD. Now, PD, you do the partitioning. Okay, this is my die. Where do I want to keep this particular logic? Where do I want to keep my CPU core? Where do I want to keep my IO? If you go back here, so you can see the partition, right? These are all the macros you have. Some can be memory, some can be logic. We're not aware. So first thing you'll do, partitioning. When partitioning is done, we'll do your power planning. We'll have the rails, power rails, VCC and VDD. You guys tell me what is your power rails or power planning? Yes, guys. Hello. Are you guys able to hear me? Okay, let's directly move into the tool. Okay, this is conformal is done. We'll say that okay, my netlist is fine. So I'll do one thing. I'll copy this netlist and go to my PD. Paste it here. This is my netlist. Let us work with this netlist. PD. And for PD, we'll use Innovus. Innovus is from Cadence. And ICC2 is from Synopsys. The newer tool is Fusion Compiler, in which all the other tools are integrated. Okay, this is the window. Let me add the design. So my design is this netlist. Edit. Netlist is added. Auto assign. Now you have to give left file. This is the tech node file. Left. Add this guy. Add the macro. Done. and you have to give the power as well. So we'll do VDD and VSS, the graph, and place it. Okay. Any questions you guys have here? So this is the window, and this is my die. You want to see, okay, what exactly I have? You can go to your this one, tool design browser, and see these are all the standard cells we have, which you have to place. These are all the wires or nets you have. Okay. Are you guys able to hear me? Okay. Let us specify our floor plan. So you have to specify your floor plan. So you were mentioning, right, W by L. Here we have height by width. So I'll put 1 by 1. And I'll give some padding as well for my IOs. Let me give 2.5, 2.5, 2.5, and apply, and that's it. So this is the 2.5. If you want to see, you can use this ruler and you can measure it. Press escape to remove it. Okay. Any query?
No, sir.
Okay. The first thing is I need power. So you have to go to power and go to power planning and add ring. So what are all the powers we have? We have VDD, VSS, right? Yes or no?
Yes, sir.
Okay. So how do you want to create a ring? Horizontal or vertical? So these are all the H means horizontal, V means vertical. What is this 1 to 10? We'll discuss that later. I'll just quickly add the layers and give some width. Let's say 0.7. I believe 0.7 will work. And we'll give some spacing as well. Let me first add all of this and give the spacing as 0.2 between VSS and VDD, and give offset as 0.5. Why this, why that, we'll discuss later. Why? Okay. What happened? Invalid net name specified. Okay. With the ruler. Haven't I done one for this one? 2.5. For planning, add ring. And IO boundary. No, one boundary is fine. Invalid net specified. What net? Okay, net. This is not added. Add it. Yes. You see this? We did in VSS. Yes or no? Okay. Let us add your strip. Now we use this strip to connect. And we are give as 0.22. I think it is set in 0.2. Set just a 5. And relative is fine. Apply. Okay. So it's loading cells. Didn't happen. What? Offset breaking is set to 0. Okay. Planning. Set the start to 1. Stop to 0. Core ring. Metal. Okay. I'm not given VDD, VSS. 5. 5. Okay. Yeah. These are all my reels. Okay. This is my floor plan. Now you can save this floor plan. Floor plan. So it will give you the name of the module. .fp. And save. See the folder. This is my floor plan. Yes. Now you can place your what you say. You can place and route your blocks cells. I'll directly jump into route. I'll not go to CTS. Special route. Any questions you guys have? I can address that. So I'll just do follow pins. I'll not do all of them. And that's it. So route is done. And let me add place optimize design. the tool will automatically try to. There's a chat. Internet connection. You'll get the explain CTS. No, I'm not going to explain CTS in this demo. So if you see, the tool automatically placed your design, your netlist, right? Now you can do your check, let's say design rule check, DRC. If I do DRC and press OK, we'll see how many violations you got. 57 violations. So you, as a PD engineer, you have to remove those violations. Once this thing is done, you'll do CTS, software synthesis, and then you'll do routing. I jumped from your placement to directly routing. And once this is done, you are satisfied with this your PNR, then you'll generate a netlist with this delay, your SDF annotated delay. Then again, you will go to the simulation stage and you'll do gate level simulation. Once this is done, you will do a sign off for physical verification. You'll do DRC, you'll do LBS, you'll do ERC. There are a lot of stuff you have. Once this is done, you can save the GDS. You can save the GDS file, and the GDS file you can send it to Foundry. Any questions you guys have? So in this course, we will start with the RTL specification. We'll do your RTL design. This is not the course for Verilog. You should know Verilog. You should know a little bit of verification understanding, the code and syntax, little bit of scripting. We'll do a lot of stuff. We'll write makefile as well. If you want, I can open the makefile. Let me close it. If you want, I can open. Where did I open the makefile? Here. It's very simple. LSC, I'm just invoking the do file, lsc.do file. If you see lsc.do file, this is my log file. So I'm reading the standard cell, I'm reading the RTL design, I'm reading the netlist, and then I'm comparing that netlist. And